G'day everyone, and welcome to the 13th annual Brian Cherry Forum. So, welcome. James, we've got the slides up there. Have I done something? There we go. Bear with me. There we go. G'day, my name is Huang. I'm your host for this evening. I've got Julianne Latham here assisting me as well. Welcome to the first round of the Brian Cherry Forum for 2021, the 3-minute thesis round. For those of you that were with us last year, it was a fantastic event, and I have no doubt it is going to be again tonight. Next slide, please, James.
Just jumping across.
That's all right. Next slide, when we can get it going. So first of all, acknowledgement of country. So we respectfully acknowledge the traditional owners of the lands in which we gather today, and we pay respects to all Aboriginal and Torres Strait Islander community elders, past and present, who have resided in these areas and have been an integral part of the history of these regions. We also extend our respects to any Aboriginal or Torres Strait Islander people present today. Next, thanks, James.
There's just a short delay on that one.
That's okay. Now, these are unprecedented times we're in at the moment. I know many around Australia are currently in wonderful lockdown. If you're like me in Melbourne, you've got a world record lockdown, but also to our friends over in New Zealand as well. You've got some COVID issues going on there. So we'll just acknowledge that lots of places around the world, and Australia as well, have got major challenges due to COVID. So please take care of yourself and those around you. Everyone thinking about everyone else and hoping that things start improving ASAP. And we can start getting back to face-to-face events and start enjoying the wonderful networking that is the ACA. So next, thanks, James. What is the Brian Cherry Award? So the aim of the Brian Cherry Award is to recognise excellence in student research, being postgraduate or final year students. It's open to any postgraduate final year students studying any aspects of corrosion, including but not limited to metallic corrosion, non-metallic corrosion, corrosion management, corrosion mitigation, and of course corrosion protection. So these are at any Australasian university. This event used to just be Victorian. Used to be an ACA Victorian branch event, so it only used to be open to Victorian students. Last year we opened it up Australia-wide, and this year we've even got some friends from New Zealand participating as well. So it's a truly Australasian event. So this award honours the late Professor Brian Cherry from Monash University in his significant contribution to corrosion education, corrosion consulting, and also just to the ACA in general. So Brian was a very big figure in the ACA. Next, thanks, James. So a brief history of the event. This was first held in 2009. So until 2019 was a Victorian-only event. Last year, due to COVID, we expanded it Australasia-wide and it went online. And we split it into 2 rounds, a 3-minute thesis and then the more traditional 15-minute presentation event. There you can see some of the past participants. With Brian and some of the pictures there. 2018 event, unfortunately, Brian passed away, so his lovely wife Miriam was there as a representative. Next, thanks, James. So, as I said, first round, 3-minute thesis. What is a 3-minute thesis? If you haven't seen one of these events before, you're in for a treat. It's a fantastic way for the students to quickly articulate their work in a 3-minute time slot with 1 slide. So what are the general rules of a 3-minute thesis event? Well, you've got to have a single static slide. So a single slide, no moving pictures, no extra props or additional electronic media, no videos, no songs. As I mentioned, 3 minutes, quite succinct little time slot to convey your work, which is very important these days when everyone has very short attention spans. In the more professional area, it's called an elevator pitch. But it's a very exciting way to learn about the work that's going on. Like all competitions, the judges' decisions are final. So if you've got any qualms about the judging, Yeah, you can take it up with me, but yeah, I might not listen. So our esteemed judges tonight, we have Dr. Ian McLeod, Dr. Karen Wilson, and Mr. Blaine McGuinness. So three names that everyone in the ACA will know. We've got good representation across Australia. Yeah, a lot of corrosion knowledge there to judge these students. So next slide, please, James. Okay, so we're going to go kick straight into the reason we're here, the student presentations. So, yep, thanks, James. Next one. So the first presentation tonight will be by Larissa. So I'm just going to move that out of the way so I can actually read it. The title of the abstract presented was a thermography inspection of undercoating corrosion from the University of Waikato. Is that correct? Hopefully I've pronounced that correctly. So yep, for the next 3 minutes, please give your attention over to Larissa. So go for it.
Wouldn't it be nice to have X-ray vision, to see through coatings, to figure out if there's any hidden corrosion underneath? Well, maybe not X-ray vision. X-ray is dangerous to humans, but what about thermography? Thermography is a lot safer for humans since it only relies on a small heat source to create a temperature difference between defective and non-defective areas. In my research, I only use an infrared camera to monitor the surface temperature and 2 camera flashes to look through coatings to inspect parts for corrosion. All right, now that I know that there is corrosion underneath the coating, how much is there exactly? Do I need to swap the part right now or can it wait? Well, wouldn't it be nice if I wouldn't even have to analyze the images? What if my computer could do it for me and tell me exactly how much of that area is corroded under that coating? No more relying on highly trained operators to look at image after image without making a single mistake, but of course, all while being consistent. And that's exactly what my research aims to do, to develop an algorithm that can autonomously look through thermal images and detect and quantify the corrosion under the coating. So I cut some steel samples, 48 to be precise, and painted about 1/3 with corrosion resistant paint. The other 2/3, I painted at different points in the experiment so I knew the extent of corrosion that I was looking for under the coating. I let all of those samples weather and corrode in 3 different environments: in salt water, in an accelerated weathering chamber, and outside in New Zealand, all for 4 months. I inspected those samples 3 times a week using my infrared camera and those 2 camera flashes. And after 4 months, I had a lot of data to sort through. After 4 months, I had 3,500 data files, each with at least 400 frames that I had to go through and analyze. So no wonder I wanted to automate as much of this processing as I could. But all that data helped me develop a robust algorithm that can go through those 480 frames and pick out the single one that shows the corrosion under the coating the best. But not only will it do that, it'll also tell me exactly how much of that area is corroded under the coating. And it'll also trace the corrosion boundaries, like it did in the image on your screen in green. So, but how do I know it's accurate? Well, at the end of testing, I paint stripped all the samples and took photos of them using a normal digital camera. I processed those images using my algorithm and compared them to the last set of thermal data that I took. And the absolute error percent is less than 1% for some of the samples, but less than 3% for the majority of them. So, are thermography goggles going to be the next new thing? Well, probably not. But sending our operators and inspectors out to detect and quantify corrosion under coatings reliably. Thank you.
Fantastic. Thank you very much. Just on the time there. Fantastic. Next slide, please, James. We'll give the judges time to scribble down some comments while we wait.
Hey, just quickly, James, would you be able to, we'll just need to swap the PowerPoints over just quickly if you want to pause the screen sharing there.
Sorry about that. I got
no problem.
I got in the zone. All right, excellent. The judges another minute or so just to quickly scribble some notes. I don't know if anyone in the audience has been a judge for these sort of things before, but you're frantically trying to scribble down scores, and let's be nice to the judges. They're doing us a favour, let's do them a favour too. How are we going, judges? Good. All right, we might kick on. So the next speaker we have is Andre from the University of South Australia, talking about assessing the corrosion performance of additively manufactured stainless steels obtained by laser metal deposition. So I'll pass the baton over to you, Andre, and go for it.
Wouldn't it be nice to manufacture metal components that doesn't rust with just a press of a button? We are actually very close to it. 3D printing or additive manufacturing of metals is already a reality in the industry. As easy as printing a document, we are now able to print complex shape parts without defects with a one-step manufacturing process. The advantages of metal additive manufacture go beyond the fabrication of new components, being also of great value in restoring largely degraded industrial parts, like those damaged by corrosion, for example. For such corrections, we have the technique of laser metal deposition, or LMD in short, which works as a welding overlay process that melts powder feedstock with the substrate by the application of a high-powered laser beam. In particular, stainless steel depositions are of great interest to industry because its ample application in corrosive environments. Still, there are some concerns on the performance of such materials that prevents the full adoption of the LMD technology by manufacturers. We have investigated the corrosion resistance of 3 printed version stainless steel grades and compared the results to its equivalent conventional manufactured counterpart. The grades that we choose represent the different types of stainless steel we can find in the market: martensitic, austenitic, and duplex. As is well known, one of the most common corrosion mechanisms observed in stainless steel is pitting. Therefore, we conduct 2 different tests to assess the pitting response of these materials under salt environment, following international standards. Our salt spray testing experiments up to 1,000 hours demonstrated equivalent or superior corrosion performance on the printed materials. Surprisingly, isn't it? But these were initial qualitative results. In a second experiment, we ran electrochemical corrosion tests that could actually identify and quantify the corrosion response of the materials. Here, all the free printed stainless steel present better resistance to corrosion than the conventionally produced alloys. The better behavior were attributed to a higher passive film stability, which is a common protection mechanism found in stainless steels. But why was this protection enhanced in the printed materials? Our further investigations revealed that the distinct microstructure produced by LMD favored a more stable passive film on the surface of all stainless steel types. Our results, therefore, confirmed that we can actually print stainless steels with better corrosion performance than traditional materials. It also affirms laser metal deposition as a mature additive manufacturing technique to structural steel parts, which will have a great impact on society by enabling a more circular economy and sovereign capability via repairing and remanufacturing of corroded parts. Thank you.
Fantastic. I had about 4 seconds to spare. That was great. Judges, we'll give you time to scribble some scores down. I don't know about anyone else, but this silence, I don't like it. I like to be able to hear stuff going on. That's why these events are usually, I like to see the audience in person, but these are the times we're in. Alrighty, we might move on. So our next presenter is Ben from the Australian National University. using automated corrosion segmenting using deep learning. I don't know how to, I'm going to say it's RustSEG. I'm sure Ben will tell us all about it. So flick on to the next slide. Ben brings his video up and away goes. Thanks, Ben. Go for it, mate.
2.5 trillion US dollars. This is the estimated cost of rust to the world's built environment every year. And this doesn't even include the cost of injury, death, or pollution. So how do we know if something's rusty? Currently, to understand when infrastructure needs maintenance and repair from rust, qualified engineers and technicians must manually inspect structures. They search the structure for rust and then determine how bad it is. But what if they didn't have to find the rust? The classifying and locating of objects and images is no new problem. Researchers have been using artificial intelligence to find and identify objects from images and videos for some time. Stop signs, bicycles, pedestrians. These can be easily identified and are now part of the core technology underpinning driverless cars. So why can't we just apply the same techniques to rust and be done with it? The answer is data. We simply don't have good labeled data sets of rust in images. In our car example, anyone can identify a bicycle or a stop sign. To build databases for driverless cars, you get thousands of people to carefully label images. One technique, for example, is the I'm not a robot test to enter a website. The problem with rust is you need experts to identify and classify it. Most people struggle to correctly identify rust. Most people are not material scientists. Labeling these datasets takes hundreds of hours, and using experts makes it prohibitively expensive. However, AI is leading rapid changes in rust detection. Researchers last year used a mix of expertly labeled and crowdsourced data to determine if an image contained rust. My work here expands on this. I've developed an algorithm that uses only publicly available photos and can tell you if an image contains rust, but more significantly, where in the image rust is located. My method, RustSEG, uses neural networks to determine if an image has rust in it. Then it goes back and asks the network why it thought that. What pixels were helpful to make that decision? What features were helpful? What features were not? RustSEG combines all this intelligence, refines its thinking, and then shows the user exactly where in the image rust is present. My AI model uses architectures that have been successful for the segmentation of medical imaging. The AI then interfaces with a module designed to understand neural network results, performing the role of a corrosion engineer, asking questions and analyzing data. The example here is trained on just 7,000 photos of rust sourced from Flickr and can determine with over 85% accuracy if rust is present, and in many cases, exactly where rust is. No human in the loop, let alone an expert. This is not image processing or color detection, this is AI. The good news is, the earlier we find rust, the longer buildings live on. This could revolutionize what we think about maintenance. My research is a significant step forward in this vision and can be easily scaled into automatic corrosion detection or enable unskilled workers to perform corrosion inspection. This is just the very first step in complex defect detection using AI. Thank you.
Fantastic. Thank you very much. All right, judges, frantically scribbling down scores. Whilst I'm just waiting for the judges, I'll at some point in today's presentation, I'll pop the link to the ACA Vic Branch Rusty Picks, hence the lovely thing behind me. The video for the talking about all the photos and the judging as well. I'll pop that in the chat. It's pre-recorded video by some of the Vic Branch members. Well worth a watch. All right. We might move on. Next up, we have Maddie from Deakin University, talking about microbiologically influenced corrosion, a topic dear to my heart. Discovering inhibitors and their mechanisms. When you're ready, Maddie, when we get the slide up, go for it.
Mined steel is one of the most construction material and largest part of the steel production in the world. However, this alloy is vulnerable to corrosion. In nature, microbes tend to adhere and attach on the surface of alloy, and these microbes can form a biofilm which cause microbiologically influenced corrosion or MIC. which is a significant worldwide problem. The cost of corrosion is $4 trillion annually, which is 0.5 trillion US dollars is estimated to be microbial corrosion. Chromite-based compounds are very effective to protect alloys from corrosion. However, these are highly toxic and carcinogenic. Therefore, it's been recently phased out. People are still using biocide to kill off the bacteria. However, these are also highly toxic and can put our natural habitat in risk. Therefore, we need to find an alternative solution to overcome this worldwide problem. We designed and engineered some advanced eco-friendly corrosion inhibitors that they can effectively protect metallic alloys from corrosion, and also they have antimicrobial properties. Advanced physical technique along with molecular dynamic simulation reveal that this material can form worm-like structure in the solution. This worm-like structure can interact with the surface to deliver engineered and customized corrosion inhibitor to make a protective film on the surface. This protective film has a double activity, both as antimicrobial or as a good corrosion inhibitor. Currently, there are no any report in terms of engineering design methodology that we can develop advanced corrosion inhibitors. Entrapment and delivery of customized corrosion inhibitor to the surface is a new technology that can protect metallic alloys from deterioration. Keep in mind that we examined our new compounds on zebrafish embryo, and these materials are environmentally friendly. This material, we are going to scale them up through Burton Molecular Company to investigate them in different coatings, and also maybe in the near future, we are going to introduce them into the world. And these are also been patented recently. Thank you.
Might have to unmute yourself there, Wayne.
That helps, doesn't it? Sorry about that. Yeah, I've just popped in the chat there, the ACA Big Branch photo competition, Rusty Picks. Sorry. There we go. There's a link to the, it's actually on YouTube, which is very handy to watch. You can watch it on your phone. Yeah, it's a good job there by Scott, Candice, and Peter Dove. Might just pop to the next slide while we wait, James, or Lockie, whoever's driving. All right, might move on. Another MIC one, fantastic. This is Hongshou from University of South Australia. The study of microbiologically influenced corrosion resistance of thermally sprayed copper-bearing stainless steel coating. So whenever you're ready, Hongshou, you can take over. Go for it, mate.
Yeah. Good afternoon, everyone. I'm Hongshou Huang. Can you imagine microorganisms like bacteria cannot make people sick, but also cause disease to the metals? Each year, the financial loss caused by the microbial corrosion could reach $1 billion. So preventing the microbial corrosion is of great economic significance. One of the areas that are greatly impacted by the microbial corrosion is the pipeline system in oil and gas industry, as shown by the first figure. Due to the unique geometry of the tube, both the outside and inside of the tube could suffer from the corrosion damage. In our project, we mainly focus on the internal corrosion because it is more difficult to detect and prevent, which make it more dangerous and risky to some degree. In the process of microbial corrosion, microorganisms attack the metals by firmly adhering on the metal surface. So the most effective way to prevent microbial corrosion is killing the involved microorganisms. In oil and gas industries, the chemical biocides is conventionally used to kill the microorganisms, but the massive application of the biocides could potentially cause the environmental damage. So to this end, we here provide a more cost-effective, long-term, and environmental friendly method to prevent the microbial corrosion in the oil and gas industry, particularly for the pipeline system. We're going to make the antimicrobial coating inside the tube, as shown by the orange color in this figure. And the coating materials we choose is the copper containing stainless steel. Copper here is added as the biocides to kill the microorganism, which will cause less impact to the environment than the conventional chemical biocides. And the stainless steel is known for the high corrosion resistance. So, so you can imagine the combination between copper and stainless steel could protect long-term protection to the tube in the more cost-effective and the environmental friendly way. Thank you.
Fantastic. Thank you very much. Just give the judges a tiny bit of time, and then we're on to our last one. It's amazing. You think 3 minutes, oh, that's not a lot of time, until you actually have to start talking for 3 minutes, and you think, oh my God, why am I talking for 3 minutes? But then you start listening for 3 minutes and it goes really quickly. It's a fantastic little snippet of information. Everyone's done a fantastic job so far. I should also mention, while the judges are having their discussions, Julianne is going to be running a bit of a quiz for everyone, just to keep everyone interested and excited online, rather than having dead airspace. So, yeah, hopefully it'll be a bit of fun. All right, I think that's enough. We'll move on. We're going to always have a bit more discussion, judges, after this. So our final talk this afternoon, this evening, wherever you want, whatever the time is where you are, is Maria from Curtin University on the optimization of double loop electrochemical potentiokinetic reactivation tests for precipitation hardened nickel alloy. So whenever you're ready, Maria, take it away.
Nickel alloys are one of the most reliable materials to extract oil and gas from aggressive environments due to their excellent mechanical and corrosion properties. However, specific batches had catastrophically failed, leading to important environmental damages and financial losses. The component cracked because a ceramic precipitate that formed within the metal. The precipitate is only a few nanometers thick, and it was too small to be detected by the current qualification methods of the alloy. This is a big problem for the energy industry, as they don't have an approach to check the quality of the alloys they buy and guarantee that they are safe to use in service. My project aimed to develop a test that can simply detect batches affected by the precipitate. To that end, we took advantage of the fact that the precipitate can decrease the resistance to a type of corrosion called integral corrosion. Therefore, we propose to develop a test that can quantify the susceptibility to integral corrosion. And the higher susceptibility we measure, the higher the extent of the precipitate the material has. The challenge was to find the right conditions that can lead to integral corrosion produced by the precipitate. To optimize the condition of the test, we compared the performance of two types of samples. The first type were a set of batches that fell in service due to this precipitate. The second set of samples were alternative batches that had a lower extent of precipitate and were successfully used in service. We tried more than 20 different conditions and select the one that showed the best distinction capability between these two types of samples. The final test is simple and safe enough that they can be performed in a wide range of laboratories, and it's also reproducible. So the industry can be sure that they can make decisions based on these results. In short, the test measure the corrosion resistance to check if a batch has a critical amount of precipitate. Today, the methods have been published and is being used around the world by both the industry and the academia. We aim to standardize the test as a tool to reduce the risk of further incidents based on these precipitates. The test will enable a safe extraction of hydrocarbons, but will also help with the material selection for future green energy production. So, in this work, we view corrosion not as a problem, but as a tool to improve the material qualification for producing the energy we need and use today. Thank you.
Excellent, thank you very much. All right, Lockie and James, if we can flick back to those other slides I had. Thank you, all the students for presenting. That was really well done. The judges now have a bit of a tough task to work out who's going to win. So judges, if you'd like to leave us there and go join your breakout room, separate meeting, whatever we have, I'll pop in and join you shortly. First of all, I'm going to give everyone a bit of background about the wonderful Professor Brian Cherry, whenever we can get the slides up. Excellent, thank you very much. So, just a little bit of background about Professor Cherry. So he attained his MA and PhD from the University of Cambridge, as did quite a few people around the world, obviously. But he was also a founding faculty member of the Department of Materials Engineering at Monash University. And he finished up as an honorary professor emeritus. A lot of people here today will have had Professor Cherry during lectures. I was one of them. He was also the Associate Dean of Research, and he was instrumental in instigating the postgraduate degrees at Monash. He was a fellow of the Australian Academy of Technological Sciences and Engineering, and he was awarded the Centenary Medal by the Australian Government in 2003, which is absolutely fantastic. His research career spanned 5 decades and included activity across all academic and research levels. It included over 100 journal articles, countless conference papers and proceedings, numerous technical reports, and in total, he had well over 250 publications. Professor Cherry's works have been cited well over 500 times by other researchers. Next slide, please, James. Early areas of Professor Cherry's research include plastics, polymers, adhesives, and later on corrosions of steel and reinforced concrete. He was a co-author of the most significant Australian corrosion publication, Corrosion in Australia, in 1983, which quantified the cost of corrosion for the Australian economy, which I believe a lot of us still quote the figures given in that report. He joined the AISI in 1969, was tirelessly an active contributor to the association with over 40 years of support. He raised the technical and social profile of corrosionists Australasia-wide. Next slide, please, James. His roles included in the Victorian Branch Committee from 1976 to 1990. That's a fair amount of time. And he was the Victorian Branch President for his period between 1982 and 1984. And he was on the editorial committee of the ACA journal, Corrosion of Materials, since its inception. That title has been passed over now, obviously, but yeah, he was instrumental in that publication. Next slide, thanks, James. In his spare time, imagine that, after all that, he even had spare time. He was the vice chairman of the Corrosion Preservation Centre, between 1988 and 2005. He was the Australian Councillor on the International Corrosion Council between 86 and 2007. Gave the P.F. Thompson Memorial Lecture in 1987. I would have loved to have seen that. He was awarded the ACA Corrosion Medal in 1995. And he gave the keynote lecture at the Corrosion Prevention Conference in Hobart in 2006. Next slide, thanks, James. But probably Brian's most important role was as an educator to generations of corrosion control practitioners. Still remember sitting in lectures just looking at him and going, oh my God, how much, there's so much knowledge in that brain. Brian's students have themselves gone on to be leaders in the corrosion field. And these include Dr. Bruce Ackland, Dr. Marita Allen, Dr. Zita Lorenzo, and of course, Professor Nick Babilis. And in addition, he had mentoring roles to the likes of Professor Maria Forsyth and Professor Bruce Hinton. He has life membership for the ACA. And one final footnote there was significant contribution to corrosion was recognised at the 2008 Wellington Conference with the award of life membership to the ACA, which is well and truly deserved. Next slide, thanks, James. I think we might nearly be, yep, we are. So I'm going to leave you in the capable hands of Julianne, who's going to hopefully run a nice fun quiz for you. I'm going to pop over and see what the judges are up to, and then we'll pop back and we'll announce the winner. So over to you, Julianne. I'll leave it in your hands.
Yeah, thanks, Wayne. Hopefully it's on.
Yes, we can. It's all good.
All right, I need whoever to share and to stop sharing so I can share. Great. Thanks.
Go ahead.
All right, everyone should be able to see my screen. So we'll give it a couple of minutes for everyone to join. So I've put the link in the chat, but otherwise you can join using that web address and entering this game code. So for anyone who hasn't used one of these platforms, the similar ones are, I think a well-known one is Kahoot. It works exactly the same way. You get points based on a correct answer as well as how quickly you get that correct answer. So speed as well as accuracy. Obviously, if you answer the wrong thing quickly, that doesn't count. Yeah, so it's 15 questions. Mostly sciencey based, but there's a few other random ones in there. All fairly lighthearted, so nothing terribly nothing technical in there. And there's no prizes for winning. It's just bragging rights, really. Unlike the actual Brian Cherry Awards, where you do get a proper prize. Give it another minute. Is there anyone that's still trying to join that isn't able to? Just shout out. Otherwise, I might start the quiz. So no one's shouting out, so I'm just going to assume everyone who wants to participate is in the quiz, and let's go. I mean, common knowledge, right? Tell me. Oh, one person got it right. There we go. Most people thought 65. Let's turn on the sound. Quickly. Oh, we're out of time. One of you? Yes, they have a lot of more bones. What do you expect? People on the board. Yep, playing computer games. Most people got that one right. Well done. There's Asian and there's 2 Africans. Yep. Let me see what over there is.
Just while you're waiting for everyone to answer that question, Julianne, if you can, well, we're nearly done. We've got 2 more questions. All right, we can wait. Karen, I might get you to deliver the result because it seems that Ian can't actually get back in. So I've just given him a call. If that's
Yeah,
okay.
there's 3 more questions.
All right, we can wait for a couple of questions.
Otherwise, I can pause at this one and resume the last 2.
If there's only 2 more questions, that's fine. How's everyone doing with the quiz? Hopefully it's tickling your brains.
What we'll do is just fast track it. No one gets to see the leaderboard. Now. Throwing some history at you guys just to keep you on your toes. All right, last question. Oh, no leaderboard. And done. Let's see who ended up taking home the win. Whoa, an upset.
Scott.
Scott Waiters.
Redraw.
Oh, is it fair when the branch president wins? Or is that the last question? Yeah, that is the end of the question. Yes. I'm not sure if it shows the final leaderboard. If I press that, we'll see what happens. I don't know. You can start delivering the results, I think, now.
All right.
Doing its thing.
I'm going to pass over to.
Yeah, there we
Oh, there's your crown, Scott. Oh, why a second, Bruce? Which Bruce though? Hinton or Ackland? Awesome, Julian. That looked like a lot of fun. Wish I could be part of it. As I mentioned briefly, normally I was going to plan to have Ian McLeod deliver the results, but there's been a glitch in the matrix and Ian can't get back in. So I'll hand over to Karen Wilson to deliver our verdict. Over to you, Karen.
Hi. You just have to guide me through this because I believe that we get 3.
Yep. So just name the 3.
So we don't have to have. There's no order. Okay.
No
So
order.
going through to.
Should actually be 4, I believe, but we'll have 3. We can have 3. Yep. Top 3.
Top 3 and withholding that we might be able to bring in another one.
Correct.
Discussion. The top 3 going through to the next round are Larissa, Ben, and Hongshou.
Yep. Fantastic. Good work, everyone.
Yep. And some of the reason that we were all basically unanimous about these 3 were because we would have loved to have been caught in an elevator with them. They were very interesting. They were passionate. They were clear, and they both left us wanting more. I mean, sorry, the 3 of them left us wanting more.
Sorry, Karen, there's just been a request to repeat the top 3, please.
Okay, Larissa, Ben, and Hongshou.
Yeah, fantastic. We might have a discussion offline. There is actually room for a 4th place in the final. But we'll have a discussion offline. But anyway, there are 3 finalists for the next round, which is the more traditional 15-minute presentation and questions. You might have noticed today's 3-minute thesis event, there was no questions. That's part of the format. Get everything across succinctly, and as Karen said, that you've got to be able to do it the same as if you were stuck in an elevator with someone. Although if you're in an elevator for 3 minutes, it's a very long ride. Unless something's gone wrong. And then if something does go wrong in the elevator, I really don't want someone talking about corrosion to me. I want to be pushing the button to get out. Excellent. Thank you, everyone that presented today. Everyone did a fantastic job. I quite like the format, and hopefully you do too. If this is the first time you've seen a 3-minute thesis challenge, yeah, now you get a flavour for what they are. It's a bit of fun. So, as I mentioned, part 2, the final, is going to be in 2 weeks' time. Same place, same channel, which is the more traditional 15-minute presentation. Get your questions ready because there will be questions for that one. Some of the other ACA events coming up, we've got the Extending the Service Life of Concrete Structures on the 16th of November. For all you concrete aficionados out there, it's going to feature 6 concrete corrosion experts. And that's free registration if you're an ACA student member. For any of these events, just go to the ACA homepage there and click on events. James, if you can pop to the next slide, please. As you would have noticed, today's event was recorded. On that ACA webpage, there's a select listing of some of the recorded events that have happened in the past. Most online events will be recorded unless there's certain sections that can't be for confidentiality or IP or other issues like that. But there are some great talks there available for anyone to have a listen back to. On joining the ACA, if there's any students here that aren't ACA members, the ACA is currently offering a special $10 membership for the first 100 students that sign up. So make a note of that URL down the bottom there, or if you need to, just click on the website. I'm sure you'll find it. If you can't find it, let me know and I'll point you in the right direction. As you can see, the ACA is a great community of like-minded people. I often find the corrosion community is very tight. There's not a lot of us. So we generally like working together. We have to, because there's no other way we can get it all done. I believe that's it from me, James. If you just want to check to make sure there's no other slides.
Yes, that's correct. We'll be finishing.
Excellent. So again, we'll be in contact to the people going through to the final with details of what exactly you need. But yeah, fantastic. Thank you so much for everyone that presented today, and thank you so much for everyone that came along and listened and joined in the quiz. And hopefully there's not too many comments in the background like, what's that guy wearing a bow tie for? Again, thank you. Go enjoy the rest of your night. Thank you to our judges. It's never easy. Thank you so much for your help. Yeah, that's it from me. Thank you. Good night. I remember the ACA Rusty Picks thing too. Go and have a look at that.